Welcome everybody. Today we will start with the second type of van der Waal forces, which is permanent dipole. But before we start with this lesson, we have to make a simple revision. In the previous lesson, we covered the instantaneous dipole-induced dipole, and we said that the instantaneous dipole-induced dipole type presents in all simple molecules in the universe. Okay, and you can check this lesson, by the way, and the link in the description box down below. Let's start with a permanent dipole. From its concept of permanent, which means like it's eternal something. So what is that? Before we start with a permanent dipole and stuff, you have to put in your mind this certain type of van der Waal forces present in polar molecules only. If you have a polar molecule, then it contains permanent dipole in addition to the instantaneous dipole. And we have a simple thing that will be covered later on, which is the hydrogen bond. Put in your mind, the hydrogen bond is a special case of the permanent. It's not a third type, but actually it's a special case of the permanent dipole. And by the way, the hydrogen bond is covered in the next lesson. So, how can I determine the type of van der Waal forces that present in any molecule that is given to you? So let's start, for example, the first one, which is CO2. Okay, from the geometry of molecules, you can check this lesson, by the way, and the link below. It has a shape of linear. Actually, it looks like this: C double bond O, C double bond O. And at that point, you have to put in your mind, first of all, is this polar or non-polar? And what are the van der Waal forces that present in here? So first of all, you have to look at carbon. All right, from the ABC of chemistry, we just noticed that the oxygen is more electronegative than carbon. That's why it's partially negative. For carbon, it's partially positive, and for oxygen, it's partially negative. And if we take the direction of the dipole, we can say that the carbon in oxygen has a dipole of the arrow is going to the direction of the more electronegative atom, and the same thing here for this bond. And since you have the same atoms, you have oxygen in here and oxygen here around the central atom, and they have opposite directions, then the dipole is cancelled out. So here the dipole is cancelled out, all right? In addition to that, because you have a symmetry, you can say that if I split this compound into two halves, you have identical parts. There is a symmetry. Because of the symmetry, the dipoles are cancelled out in here, and that's why we can say that the CO2 compound or molecule is non-polar. The only type of van der Waal forces that present in this molecule is instantaneous dipole-induced dipole. I just want to abbreviate this long name. Don't write it in the exam. And just like for me, because I'm giving the lesson, I will explain it by ID. Okay? Don't write it in the exam. Let's take another compound, which is H2S, for example. So I just want to draw this compound. We just noticed that the sulfur atom present in group number 6, and that's why it has 6 electrons around itself. We have 2 hydrogens. Okay, then we have hydrogen here, and we have another hydrogen. In other words, the shape of this molecule, as we learned from the ABC of geometry, is nonlinear. Okay, how can I determine the direction of the dipoles at that point? First of all, you just notice that sulfur is more electronegative, and that's why it has a partially negative. For hydrogen, they're partially positive. And if you just draw the direction of theirs, they'll be like towards the sulfur atom in here, and this one is going to be towards the sulfur. And put in your mind, we have lone pairs, and that's why their direction is up as well. So at that point, since you have directions like this and this and this, the overall direction of the dipole is up like this. And that's why we can say, since you have a dipole, they do not cancel out each other. We can say the H2S molecule is polar. Okay? And the reason behind, we don't have symmetrical cloud of electrons around this molecule, because you have a lot of electron density in here, and they're not like is an overall symmetry. So you have to put in your mind the nonlinear shape is asymmetry, which is the opposite of symmetry. It's asymmetry. And as a result of that, the dipoles at that point do not cancel out each other. do not cancel out each other. And as a result of this, this is polar, and the types of van der Waal forces that we have, which is the instantaneous dipole-induced dipole, write the whole name. I'm just giving you the abbreviations because I'm giving a lesson, it's too long. Instantaneous dipole-induced dipole, and the second one, which is the permanent dipole, permanent dipole. We have two types of van der Waal forces at that point. Let's take PH3. All right, so can I draw the shape of this molecule? First of all, you have to draw the phosphorus atom. Actually, it's in group number 5, which means it has 5 electrons around itself. We have hydrogens, we put those hydrogens around like this. And we can deduce that it has a shape of trigonal pyramidal, in which we have it like this. And by the way, the shape in here is a trigonal pyramidal because it looks like a pyramid. And if we write the direction of like electron clouds or the dipoles, they're going this. Since the phosphorus is more electronegative, in addition to those electrons, they're going up, and that's why the overall dipole is going to be up like this. And since we have a dipole at that point, then the trigonal pyramidal is asymmetry or asymmetrical, and as a result of that, the dipoles do not cancel out each other. Okay, since they do not cancel each other as a result of asymmetry, then this compound here is polar. And as a result of its polarity, it contains two types of van der Waal forces, which are the instantaneous dipole-induced dipole, in addition to the permanent dipole. So we have two types of van der Waal forces at that point. Let's take BF3, for example. All right, so let's draw the BF3 at that point. B has 3 electrons in its outer shell since it's in group number 3 from the periodic table. All right, and we have 3 fluorine atoms. Okay, we have lone pairs. I don't care about that. Doesn't matter to me. Then we can deduce that the shape of this compound is trigonal planar. And if we want to draw the dipoles, we can say that the fluorine is more electronegative, then it comes like this. For here, it comes like this, and this one comes like this. Those two arrows have a dipole towards the opposite direction of this one. Like the net resultant of those two is going to be like this. And since we have those that are in the same magnitude and opposite to each other, they cancel out each other. And at that point, we can say that the trigonal planar is symmetrical. And since it's symmetrical, the dipoles cancel out each other. I'm sorry for my handwriting, they cancel out each other. And since they cancel out each other, then the BF3 molecule is nonpolar. And since it's nonpolar, then it contains only one type of van der Waal forces, which is an instantaneous dipole-induced dipole. All right. Okay. Let's take another one, which is, let's say, CH4, which is methane. And if you remember, it looks like this. Carbon, it has 4 bonds. Yeah, it's discussed by the way. And by the way, the direction of the dipoles, I'm going to explain it to you in this way. This one is going to be like this. All right. And this one comes like this. If you check the extension of the two, like here, those two, they have a direction of like this. And those two in here, they have a direction like this. Since at that point we have 2 identical atoms with opposite directions, and that's why we can consider that tetrahedral shape, which is the shape of CH4, is symmetrical. And since it's symmetrical, the dipoles, okay, cancel out each other. And since they cancel out each other, then they are non-polar. molecules. And the only type of van der Waal forces that we have in here is instantaneous dipole, induced dipole. And by the way, the instantaneous dipole here has another name, which is, it could be one of these or three names. We have London forces, or instantaneous dipole, induced dipole, in addition to the temporary dipole, okay, which is the opposite of the permanent. Let's go to the last one, or before the last one, we have PCl5. You just remember from the lesson of geometry, it has a shape of trigonal, bipyramidal. And let's draw it. We have P, we have like, this one looks like a spinner. We have Cl, and we have one up and one down. Okay, let's draw the dipoles. The Cl is more electronegative than the phosphorus atom, and that's why you have the first two dipoles that cancel out each other at that point. They cancel out each other here. And those two dipoles have a net resultant of in the middle, and this one cancel this one. And which means that the PCl5, a trigonal bipyramidal, is a symmetry or symmetrical. Since it's symmetrical, the dipoles cancel out each other. Okay, and since they cancel out each other, then this is nonpolar. Since it's nonpolar, then it contains only the instantaneous dipole, induced dipole. And the same thing is repeated for the octahedral. Which is a simple example like SF6, for example. It's the same story. We have S in the middle, we have a square in here, and one up and one down. And you have 6 F's in here. All right. They have opposite direction. Okay, this will cancel this and this. Okay, you can see that all of the dipoles, since it's symmetrical, okay, the dipoles cancel out. Okay, and that's why it's nonpolar. Since it's nonpolar, then it contains only one type of van der Waal force, which is instantaneous dipole, induced dipole. You have to put in your mind. You could have, as we said, that the linear should be symmetrical. What do you mean by this? I just want to give this example, like H, C triple bond, and this is an acid, a weak acid. Since it's linear, but you should have, in addition to be linear, you should have a same dipoles that cancel out each other. If you compare this one with this, both are linear, but the HC in here is polar, and this is nonpolar. If you have identical atoms around the central atom, in addition to symmetrical geometry, then it's nonpolar, like this. But if you have different atoms around the central atom, for sure, regardless it's linear, this is a polar. The magnitude of dipoles of those two bonds are not equal, and that's why it's polar. Okay, this is very important point.